This lecture is part 3 of section 3.5 from Math 311, a course in linear algebra at Western Illinois University. So we are about halfway through this big section on subspaces, bases, dimension, and rank. And in fact, in this lecture, we're finally going to define what those three last words are. Okay, so we have already talked about subspaces and subspaces associated with a matrix, like row spaces and column spaces and null spaces. All those subspaces are infinite, have infinitely many vectors in them. So you can't write all of them down. So if you want to describe a subspace, you need to sort of describe it by a list of spanning sets or generators. Vectors that will such that all linear combinations of this set of vectors will produce the desired subspace. But you don't want to just give any spanning set, because some spanning sets are a little redundant. So you'd like the spanning sets to be as small as possible, but still generate that subspace. And that's what happens when you have when they're linearly independent. So what you're really looking for to describe a subspace is you want a spanning set that's also linearly independent, and that is what we call a basis. So that brings us to our first definition here. If S is a subspace of Rn, then a set of vectors is a basis for S if S is equal to their span and the vectors are linearly independent. So for example, we know that the vectors 1, 0 and 0, 1 is a basis for R2. These are clearly linearly independent. They're not multiples of each other, and any and the ordered pair xy can be written as x times this plus y times this. So it's a basis. It's actually called the standard basis of R2. But R2 also has another basis. We also described how 1, 1 and 1, negative 1 also is a basis for R2. These are clearly not multiples of each other, so these are linearly independent. And this will span all of R2, right? I think we found that xy was x plus y over 2 times 1, 1 plus x minus y over 2 times 1, negative 1, I think, and that works. Okay, so this is a basis, another basis of R2, and we're going to see that the basis is not unique. The same subspace can have many bases. This is not a basis of R2, because we can see that these are not linearly independent. 5, 1 can be written as 5 times this vector plus 1 times this vector, right? Or another way of looking at this is 5 times this minus 5 times this plus minus 1 times this plus 1 times this vector is 0, 0. So it's not linearly independent. These three vectors, is a basis for R3, because any triple xyz can be written as x times this plus y times this plus z times this. And these are clearly, I think you can see that these are linearly independent. The only way that something times this plus something times this plus something times this is 0 is if all these somethings are 0. Okay, so they're linearly independent. So it's a basis. These two vectors, even though they're linearly independent, they are not a basis, right? Because any linear combination of these vectors will have 0 in the third component, right? So it doesn't cover all of R3. Okay. So remember, these things both these conditions have to work. Okay. What's next? Okay. Some more specific examples. We can see we talked about planes when we were at the various forms of describing planes. We said that in some cases, if you had a plane for the origin, you could write that every element in this plane as a linear combination of two vectors. And in fact, for example, this any xyz satisfying this equation will be a linear combination of this vector and this vector. In fact, you can, basically you can get this by just solving this equation using Gaussian elimination, right? This would just be use the matrix where you have, one row and 3 columns, and use Gaussian elimination there. So not surprisingly, a plane is, well, we'll talk about dimensions soon, but this is a two-dimensional object. We require two elements in the basis. A line in R3 is can have a basis consisting of one element, one vector, because we know that every, for example, this case, the subspace of a line where the direction vector is 2, 3, 5, well, every element is really going to be some real number t times this vector, right? So so here we have a basis that just consists a subspace in which a basis consists of a single element. Okay. All right. So there are lots of bases for different subspaces. However, we're going to see now that even though the basis of a subspace is not unique, the size of the basis is unique. And let's just see why that's true. Now, the proof in the book is a little, describes it in a little more detail. I think what we're going to do is we're just going to show why we can't have we're going to do a specific example why things go bad if let's say if we have a subspace where we have a basis of 2 vectors and another basis of 3 vectors, and we want to show what happens when that happens. So if, let's suppose, if these two vectors, u1, u2, and actually let's make this v1 and v2, and u1, u2, u3 are bases of a subspace S. Okay. Well, in particular, what that means is that everything here, because everything here is an S, so these are an S, so these are going to be linear combinations of everything here, and everything here, each element here is going to be a linear combination of these. So in particular, U1 is going to be something times V1 plus something times V2. So we'll say A11 V1 plus A12 V2. And U2 is A21 V1 plus A22 V2. And U3 is, say, A31 V1 plus A32 V2. Okay? For some real numbers, Aij. Okay. All right. Now, what we're going to do is, let's suppose, what we want to do is we're going to take an arbitrary linear combination of these u's, and we're going to see that they're going to be linear combinations of these. Okay. So if, let's say we have three numbers, C1, C2, and C3, such that C1U1 plus C2U2 plus C3U3 is equal to 0, then we can do a substitution, and we get C1 times this plus C2 times this plus C3 times this equals 0. Okay, so that's just by substitution. And now we can write everything. This is actually going to be a linear combination of V1 and V2. So this will be C1 A11 plus C2 A21 plus C3 A31 times V1 plus C1 A12 plus C2 A22 plus C3 A32 times V2 equals 0. All right. Now, since V1 and the set V1, V2 is a basis, and we have this linear combination equals 0, and because they're linearly independent, that means this big number here and this number has to be equal to 0, since V1, V2 are linearly independent. Okay. So writing this another way, we can actually write this as in another as a homogeneous system of linear equations. This is A11, A12, A1, I'm sorry, this is A21, A31, A12, A22, and A32. Equals 0. All right. Now here's the catch. Let's see if you can think about what the problem is here. This system, this is a homogeneous. This represents a homogeneous system of linear equations. It's going to have infinitely many solutions because you have 2 rows, 3 columns. You're going to if you were to do Gaussian elimination, you get at least one non-pivot column, so you get one free variable, right? So this has infinitely many solutions. Okay. All right. Well, why is that a problem? Well, that means that we can find some non-trivial solution. There's going to be some, if there's some non-trivial solution here, that means then we can find that we get some non-trivial linear combination of the u's equal to 0. Well, that then contradicts, we assume that U1, U3 is linearly independent because it's a basis. Okay, so this contradicts the assumption that U1, U2, U3 is linearly independent, right? Right. All right, because if we can find a non-trivial solution here, we get a non-trivial linear combination here, which is 0. Okay, and that shows that this, if this is a basis, this can't be a basis. And basically, we can repeat this argument whenever we have 2 bases of unequal size. Okay, we just do this thing. We take the vectors in the bigger basis and write them as linear combinations of the vectors in the little smaller basis, and then we get a rectangular matrix like this, a system like this with infinitely many solutions. Okay, so that's why the number of elements in a basis is unique, and that number is called the dimension of that subspace. So we get the official definition is that if S is a subspace of Rn, the dimension of S is the number of vectors in any basis of S, and we just know it by dim S. Okay, so the dimension of Rn, now surprisingly, is n, because, for example, we can just take these vectors where all the components are 0 except one of them, right? This is actually called a standard basis, and sometimes we denote this one by E1, E2, En. Okay, this is a standard basis of Rn. You can clearly see these are going to be linearly independent, and they span all of Rn. The dimension of the trivial subspaces, we just give it, by convention, we call it 0. Technically, this does not have a basis, right? We don't really want a basis can only have non-zero vectors, right? So we just define it this way. Not surprised, a plane in R3 is going to have dimension 2, and a line in R3 or R2 is going to have dimension 1. That's what we saw in the previous example, right? Okay, so that's the basis. Now, we want to do this is we want to, how can we find a basis of a given subspace without guessing? Well, for rows, if the subspace is a row space or a column space or a null space, it's actually not too hard. There's actually a nice standard way to do this. And that's what we talk about in the next page. And I made this a theorem because it's really important. Your book actually just lists it as something different than a theorem, but it's very important. So if A is an m by n matrix and B is the reduced row echelon form of A, then the basis of A, we can take the non-zero rows of B to be the basis of the row space of A. For the base, to get a basis of a column space of A, we take the columns of A corresponding to the pivot columns of B. So remember, the pivot columns are the columns with the pivots on them, with the leading ones in them. And so if the pivot columns are the first, second, and fourth columns of B, then we would take the first, second, and fourth columns of A, and that would be the basis of the column space. And then finally, to find the basis of the null space of A, well, we basically find the null space and set Bx equals 0 and solve for that, and write everything in terms of the free variables. And it's sort of business as usual in the sense that we've already done this before. Okay, we just have to take it maybe one step further, and we just give the vectors without the variables. So let me give you an example of how we do this. We have a 3 by 3 matrix A, and we're going to just reduce this to use elementary row operations to find this reduced row echelon form. We'd like a 1 up here. We can interchange the third and first rows. Okay, so we'll get 1, 2, -1, 2, -1, 0, 1, 2, -1. And then we would like to, oops, and I made a mistake already. This is 3, 1, -1. Okay. All right. Then we want to get rid of the 2 and the 3, so we'll multiply -2r1 and add that to r2, and multiply -3 by r1 and add it to r3. And what we get is 1, 2, -1, 0, -5, 2, 0, -5, 2. If we do everything correctly, just remember, for example, like -2 times 2 is -4, plus -1 is -5, and so on. And right away you can see that this with the third row and the second row are the same, so we can just basically replace this with all zeros, or basically add -r2 plus r3, and we'll get 1, 2, -1, 0, -5, 2, 0, 0, 0. And we'd like to make this entry a 1, so we'll multiply this row by -1/5. So we get 0, 1, -2/5, and then 0, 0, 0. And then finally, we want to get rid of this 2, so we'll multiply -2r2 and add it to r1, and we get 1, 0, and then this is going to be positive 4/5 minus 1, that's -1/5. And we'll have 0, 1, -2/5, 0, 0, 0. Okay, so this is in reduced row echelon form. I have some fractions. That's okay, we can deal with them. But now we can see that these rows will be a basis for the row space. Now you can clearly see, I hope it's clear that these two rows are linearly independent. Okay, they're not only are they not multiples of each other, but because we have a 1 here and a 1 here, basically. basically all the non-zero rows of a reduced row echelon form have to be linearly independent if you think about it. Okay, so the basis for the row space of A will be this, for the first row and the second row. Basis for column space of A, what will that be? Okay, so in this case, we can see the pivot columns are right here, right? These two are the pivot columns because of we have a pivot here and a pivot here, right? Remember, a pivot is the first non-zero entry of a row, and that's always got to be a 1 if it's in reduced row echelon form. So it's the first and second rows, or it's the first and second columns here, and so we take the first and second columns of A. We get 3, 2, 1, and 1, negative 1, 2. Okay, it would not be all 3 columns. In fact, if you think about this, or I'll just show that 1/5 times 3, 2, 1 plus 2/5 1, negative 1, 2 plus negative 1, 0, negative 1. That's going to be 0. That's going to be 0. So the columns of A are not linearly independent. They're actually dependent. Okay. Now, where did we get all these fractions from? We'll get there. We'll get there in a moment. First, finally, let's find the basis of the null space. To do that, we just take this reduced row echelon form and just replace write the corresponding equation. If we let the variables be x, y, and z, let's say, what this means, and if we set this matrix times x, y, z equals 0, what we get is 1x plus 0y minus 1/5 z equals 0. Then this would be 0x plus 1y minus 2/5 z equals 0. And then 0 equals 0, we can just write this as z equals z if we want. So we would get x equals positive 1/5 z, y equals 2/5 z, and z is our free variable, so we just let z equal z. Now this is where we would stop here if we were just trying to find the solution to the system of linear equations. But because we're trying to find the basis of it, we can see that this is really going to be, you can see x, y, z is going to be z times this vector 1/5, 2/5, and 1, right? Okay. Okay. And this is the vector that we want to be our basis. So in fact, our basis of the null space of A is just going to be this column vector 1/5, 2/5, 1. Right, so the dimension of the null space would be 1. The dimension of the row space and the column space are both 2. Okay, and we're going to see in very soon that this is no accident. So I want to just show that this. Where does this come from? Why can we get away with this? Okay, this is a very important process. You want to memorize this. You want to know how to apply it, do the calculations. But why does this work? Okay, because I want to. I don't want you just to take my word for it. Okay, that's not what math is about. Okay, go on to the next slide. Why does this work? Well, for the first case, we talked last time that doing elementary row operations doesn't change the span of the rows. So we know that the row space of A and the row space of the reduced row echelon form of A is the same. Okay, and we also know that the non-zero rows of the reduced row echelon form of A must be linearly independent. And the reason why that is if you think about it, let's say we have something like this. Okay, like this. Let's say we have, these are the rows. We can see that these three rows have to be linearly independent because they, if we take something times this row plus something times this row and something times this row, if we want the first component to be 0 and we want the whole thing, if we set that whole linear combination equals 0, the only way the first component can be 0 is if the first scalar is 0. And the only way the second component can be 0 is if we're multiplying this row by 0. And the only way the fourth component can be 0 is if we multiply this row by 0. Okay, so that's why the non-zero rows are going to be linearly independent, so they span the row space, and so they're a basis. Now, for the column space, it's a little more complicated, but not too much. The columns, the elementary row operations do change the column space. However, they don't change the dependence relation. What we're going to see is if we do elementary row operation on a column or on a matrix, and there's already a dependence relation among the columns, then there's still going to be a dependence relation on that same dependence relation is going to hold for the columns of the new matrix. That is, and why is that? So if we have, let's say, these AIs represent the columns of A, and if there's some linear combination of these equal to 0, if we multiply an A by an elementary matrix on the left, which remember that has the same effect of doing an elementary row operation on the matrix, then we get this is EA1, EA2, EAN, and we can basically do a matrix operation. If we take this first original dependence relation and multiply everything on the left by E, well, here we get E0, which is 0, and then here we'll have, because the C's are just real numbers, they're scalars, we can pull them out and break this up. This is EA1 plus EA2 and so on, right? So we're going to get the same, we're going to get the same dependence on the columns here are going to satisfy the same dependence relation as the columns up here. So if the columns of A are already linearly dependent, then the columns of the new matrix will be linearly independent. And similarly, if they're already independent, then they will be independent in the new matrix, right? So if you just think about this, it's in the reduced row echelon form, it's very easy to see that there's no way that, we can see that this column, and this column have to be linearly independent, right? So it's impossible. So the original matrix, the first, second, and fourth columns of the original matrix had to be independent, because if they were dependent, then that same dependence relation would hold for these three columns here, which obviously they won't happen because they're literally independent. Okay, so that's why this works. Okay, so it's not, you get once again we see what a powerful thing reduced row echelon form is. All right. Now, a little more theory here. So the row space and the column space are going to be different, but their dimensions are going to be the same. And in fact, they're going to be the same as the rank of a matrix. Remember, we define the rank as the number of non-zero rows of the reduced row echelon form. So let's just think about this. So why would this be 2? It's going to be what these three quantities are all equal. It's because the rank of A is equal to the number of non-zero rows of its reduced row echelon form. Okay, that's the definition of the rank. Well, we can see that this is also equal because every row has a pivot. And that we can see the number of pivot rows is going to be equal to the number of pivot columns. So. Okay. And we just saw that these rows, the number of pivot rows, we see that's going to be the dimension of the row space of A. Actually, we could sort of see it right here, because the non-zero rows of the reduced row echelon form is a basis, so we could actually go say this is equal to this. Well, we also see the number of pivot columns of reduced row echelon form. That's going to be equal to the dimension. This is going to be equal to the number of vectors in a basis of the column space of A. Right? As for example, we would take the first, second, and first, third, and fourth columns of our original matrix to be the basis of the column space. So that's going to be the dimension of the column space. Okay. All right. So that's what it basically boils down to. Because the number of pivot rows is equal to the number of pivot columns. And it's reduced row echelon form. As far as the null space goes, the nullity of A is defined as the dimension of the null space of A. And if A is an n by n matrix, the rank plus the nullity is always equal to n, and is the number of columns in the original matrix. This is called the rank theorem. This is another one that you want to remember, very important. And the reason why that is true, well, we just found that the rank is equal to the number of pivot. Well, it's equal to the number of pivot columns, pivot rows, but it's also equal to the number of pivot columns of A. And the nullity is the dimension of the null space, which is the number of free variables in solving AX equals 0. Okay, remember in the previous example we had one free variable, so the nullity was 1, and we only had exactly one vector in the basis, right? So we basically, the number of free variables is going to be the nullity, but this is also equal to the number of non-pivot columns of the reduced row echelon form. Okay, I think I should have said this is of the reduced row echelon form of A. Okay. So we have the number of pivot columns of the reduced row echelon form plus the number of non-pivot columns. Well, that consists of all the columns, right? So this is equal to the total number of columns of the reduced row echelon form of A. And of course the reduced row echelon has the same number, is also equal to the total number of columns of A. So which is exactly n. Okay. So that's why the rank theorem works. Okay. All right. This is pretty intense, right? Okay. I think probably you let this digest, do some problems, get some practice finding these bases, and we will see you next time.